Good morning. My name is Todd Toles. I am the CTO of the Modern Infrastructure team. My focus specifically is high-end storage, and today we're going to talk about one of our high-end storage products called XtremIO X2. I've been here since 2007 and was one of the original XtremIO team members in the pre-sales role. So also want to introduce.
Hi, I'm Zvi Schneider. I'm the chief architect for XtremIO. I've been with XtremIO from 2011, late 2011, different roles within the engineering, and currently having the role for about an year and a half of the chief architect.
So first off, let's go into what is X2. Stephen is right? So we've done a lot of work on modernization of XtremIO X2. However, some of the core pinnings of X1 have been continued to X2, right? So things like consistent performance. Everything we're doing, and as an X1 and X2, is all done inline, right? So all our data services, be it data reduction, be it compression, deduplication, snapshots, all of that is all done inline, right? So efficiency, right? So as Vince mentioned earlier in the VMAX all-flash presentation, XtremIO gives us unparalleled efficiency. And we'll kind of talk about that and talk about some improvements that we've done in X2. And finally, application integrated copies, which is a stellar function of XtremIO. Let me give you an example. So one of my customers runs an Oracle database. It happens to run pricing for a fast food company. Every time they have an application problem, it's an Oracle database running Oracle applications. Every time they have an application problem, they make a copy of that database. In the past, they could make about 4 copies because they had to make a physical copy, right? It's being very expensive. Last I looked, they're making 80 copies with XtremIO. So 10 terabyte database, 80 times, about 800 terabytes of space. 13U in an XtremIO configuration. So very dense, but all integrated with the application. So if they want to make a copy, it's completely integrated. It drives through VMware, and they instantiate another copy to their development farm. The developers can take a look at it. When they're done with their testing, they get rid of the snapshot, and everybody goes back to normal. So that's one of the things that we deliver with XtremIO, both in X1 and now here in X1 and X2. So what are we doing, right? So we design goals, right? So you always have goals when you do a new major release. So our goals were certainly to take the best of XtremIO and make it everything better. And we looked at and we listened to you, the delegates here, as well as our customers, and said, all right, what do you want? What are you looking for in the next evolution of XtremIO as we move to X2? And we kind of settled on 5 areas of innovation. Those 5 areas of innovation, we heard loud and clear. We wanted the ability to go ahead and be more flexible in our ads, right? So in the past, you basically had to add an X brick or a pair of X bricks, which is 25 drives at a time. Next to, we said, all right, let's make it a little simpler, right? So we can certainly can still continue to add X bricks, but we can also add drives. So we can add drives in as few as 6 drive increments. And we'll talk about that as we go through. We wanted to innovate on the software because that's always important, right? That's where really the secret sauce is. We're doing commodity hardware, nothing proprietary in the hardware itself. So we wanted to innovate on that. And Zvi is going to talk a little bit about that. One of our features called Write Boost. That's innovation on that. The second is we wanted to double down on ICDM because we think it's an important use case. Because customers have lots of copies of data, right? So if you talk to some of the industry, like IDC, for example, would say 60% of data is copies. So we wanted to innovate on that, and we wanted to take advantage of that. The customer example I gave you before is an example of that. We wanted to have a completely HTML5 UI, and we've delivered on that. We've actually delivered on that both in X1 and X2, and removed the last vestiges of Java from the product. Because we know everybody loves Java and all the security issues associated with that. So,
Drinking Java.
Yes. I am not a Java drinker. I'm a soda drinker, so I've been no Java on the no Java bandwagon for a long time. And then finally, we want to innovate on the areas of replication. So take and leverage what we're already doing with our snapshot technology and leverage that to do native replication where customers are looking to go ahead and do that. All right, so let's look at kind of the architecture, right? So things that are the same from X1 to X2, right? So scale out. Our metadata and our content addressing, everything we do is done in memory. We're not doing metadata destage or metadata cache, where we cache the metadata and if things get busy, we have to destage out. We don't want to do that. And the reason why is consistency of I/O. So if we're looking at consistency of I/O across the platform, we want to know it's very deterministic. And we're giving you some very excellent, in X2, for example, and I'll show you a couple examples of that, we're delivering response times in the 0.2, 0.3 millisecond response time, so very quick from a response time standpoint. And of course, we want to do that while keeping all the data services intact and doubling down on them, so doing some enhancements in the compression area, for example. All right, so how things work, right? Just kind of a review for those of you who are not familiar with XtremIO. Our technology is all based on content aware. We have an incoming data stream, and we run it through through what's called the content engine. So the first thing we do is we do a fingerprint. One could call it a hash, but it's a fingerprint, right? So we only want to make sure that the unique blocks are written to the flash media and written once. One of the things that you always have to be concerned about in all flash is write amplification, right? So if you're writing data to disk, and later on you're going and doing some processing, you're coming back, and you're moving things around, one of the things you're doing is you're stealing away performance because you're doing write amplification. The second thing is you're consuming flash media, which endurance becomes an issue. And then finally, we want to be very on the performance, be very consistent. So we do everything so that we only write the data to the flash media once. All right, so let's kind of take some blocks of data. All right, so I've taken some blocks of data, just some random, our hashes are much longer in this, but the purpose of discussion, let's make them very small. We go ahead, in this case, we're going to take just the first byte and kind of look at that across, and we're going to use that to distribute across the environment. And that's the core of how XtremIO works. So we like to say everything in balance across the environment. And for the CPU, memory, and disks. And this is the core technology of how we do that. We use that hash to go ahead and balance across our environment. Let's kind of take an instantiation of that, or look at that. So one of the things is we of course support multiple XBricks. Remember, everything has multiple controllers. So in this case, it's 2 XBricks, 4 controllers. Over 50% of our install base is multi-controller. So it's not just, hey, we just have a single XBrick with 2 controllers. Over 50% is multiple controllers in the environment. So let's take that incoming data stream, and I'm taking kind of just a nice first byte. I'll just look at it. And the algorithm does a lot more than that. But for purposes of illustration, we'll just use that first byte. So we're going to take that first byte and we're going to distribute it across the environment, such that each of the controllers has a small component of it, right? So it's split out so that it's evenly balanced across the environment. But now take that same data stream that came in across the environment. And now if you notice, there are 2 that are the same, right? They're in kind of a little darker blue here in the environment. And we're going to kind of process them through, right? So we're redistributing them, and we say, all right, based on the first byte, here's what I want to do. So I'll go through and say, all right, this particular block goes here, so forth, and so on. And as we're doing that, as the I/O is coming in, we're not doing it in post-process, we're not doing it later on, we're doing it as we go.
But you are doing it in one of those controllers.
I'm sorry?
You are doing it in one of the 4 controllers in the 2 bricks down there, because you're making it look in the animation like it's an external process.
No, yeah, it is. Yeah, it's happening across here. But for example, if these strings came through, right? Let me kind of go back through here. If these strings came through here, they could be coming across multiple interfaces. They don't have to come across all in one stream, all across one interface. Remember, everything gets all balanced across the environment.
I get it.
Yeah, there's no magic cloud. Right? No, absolutely. No, it's the XtremIO operating system that operates in a distributed fashion. That make sense?
Yep.
Okay.
So Todd, the assumption there is that each brick controls an area of the address space of the range of fingerprints that you build.
Yep.
When you expand and you add in new bricks, then
Yes.
clearly there's a distribution that needs to happen to reallocate the address
Absolutely.
space ranges. So Ed, how does that happen if you're going to talk about that?
Sure.
I'll obviously not preempt, but what happens for the stuff that's already written, and how does that lookup for stuff that now is potentially on the wrong brick managed? Is that done through lookup, or is that?
Yeah, so actually let's talk about it. I think it's an excellent opportunity because it's an important question because we're talking about multiple controllers.
Yeah.
So first off, let's take the easiest scenario, which is not the question you asked, but I'll talk about it first. What happens if one of these controllers fails? I'm taking the reverse, right? You're saying, well, I'm adding. Well, also we have to subtract, right? It's hardware. Eventually it's going to fail. So let's say for purpose of discussion, this particular controller fails. What happens is these will be redistributed across the environment. And what we will do architecturally is say, all right, this guy has to support the back-end disk a little bit more than the other ones because he's going to be talking to the back-end DAE. Might be easier for me to draw it.
We like whiteboards.
Hey, whiteboard.
Vince, I think you got through that without doing a whiteboard. We definitely have to fix that. All right, so XBrick 1, XBrick 2, storage controller 1. I will try to draw a little bigger for those of you on the web stream. My apologies. All right, and we have, of course, multiple for the back-end disk. And in X2, we haven't got to, but we'll talk about it a little bit. But now we go between 18 and 72 disks. But let's say we have 18. Then we'll talk about your expansion. So we have 18 drives in here, right? So we're full. All right. So what happens here is, let's say this particular controller fails. What happens is its memory space. It's inside XtremIO. There is kind of a front end, mid, and back end processing. It's RCD is our name for it. And what happens is we go ahead and redistribute that. So we know that, for example, if this storage controller fails, this guy has to do more work on the back end. Right? So it's not smart for me to just go say, hey, you know what? This partner pair needs to take all the work. That's dumb, right? We don't like that. So let's go say that this guy's going to do some more D work, some back end work. These guys will take some of the C work from this guy, kind of the mid-plane work. So, but what will happen is, if, for example, before we were at, let's try to do this to make my math easy, right? So if we were at 50%, 50%, 50%, and 50% from a CPU perspective, so it's 200%. If I take this guy away, each of these guys, if I do my math right, should be about at 67%. So we rebalance across the environment. So it's a little different than a dual controller architecture, right? So in a dual controller architecture, if this fails, I got to take everything over here, right? So I'm doing intelligent failover to failover logically as well as physically. So let's take your second question. Which your second question?
I'd add something just to clarify. So in this specific scenario that Todd mentioned, so obviously we don't relocate any data.
Yep.
So we use the redundancy of the other storage controller to access the data. What we do use is the architecture of XtremIO with the two layers. We have the logical layer, which is also segmented and distributed, and the hash space, you can call it layer. So the hash space must stay here. So this controller does more work now, but in order to balance this, because we have this ability of scaled architecture, we can move the logical pieces and spread them around and make the impact of this failure to be 1 over n and not half for some of the I/O.
Yeah,
so that's what he's talking about. So here there will be no data relocation, obviously, yeah?
So it's
only
it's a bit
metadata
like
that will be balanced.
when you talk VMAX, sorry, I know we had VMAX earlier,
okay.
but when you look at VMAX and you lose a director, then you lose a 1 over n of your performance. You're talking about something that gives a similar sort of architecture where loss of an individual controller doesn't adversely affect you, only lose that one fraction.
Yeah.
Okay.
It doubles down upon it.
But what's the actual impact when that occurs in terms of performance then? How long does that relocate and that rebalance process take, and what does the end user see?
So what we are talking here about is only kind of rebalancing of logical space. This happens really quickly. It's not about moving data, so it's a very quick process.
What's really quickly? Because
doesn't have to reload hashes from the other guy?
yeah.
No,
it doesn't.
It does
lazily reconstruct the.
Is it like microseconds?
I'm sorry?
Is it microseconds before it happens?
It's more of I assume seconds or something.
Yeah. So basically, what happens is we need to go ahead and redistribute across and reprotect journals, for example. That has to happen before we take any more I/O, because that's got to make sure that we're still protected.
That's why I was asking the question.
But the metadata, as V mentioned, loads later, right? So that all we have to do is basically say, all right, recompute where things go, move them around, and then go ahead and make sure I've reprotected journals, and then I basically start up. So that's a short process, right? So that's measured in a second or two.
So SC2 on brick 2 fails.
Yes.
Reads to the data that's on brick 2 are processed by SC1.
Yeah.
Because that's the only place the data
Yes.
is.
Yes. True with almost all multi-controller architectures.
Yeah.
So writes, but brick 2 was responsible for some range of the hash space.
Correct.
So you're temporarily reallocating some of that hash space to other bricks?
No, hash space is still managed here. So we have hash space and logical space.
Okay,
The hash
so-
space must be attached to must be on a controller that physically sees those
Okay,
drives.
so
The
as I
logical
write-
space,
Yeah.
this is kind of additional optimization to really balance the resources that we move the logical space here. Yeah.
Okay, let me go through.
Yeah.
So
It's a piece of lunch.
I write data that's in the hash space that's managed by brick 2.
Yeah.
SC1 still handles that. SC1 on brick 2.
But the back end, yes.
The
It's
back end,
basically
yeah.
like the D, which is the back end, the workload. But remember what happens
Okay,
is
but
in converse.
But we've taken from SC1 the connect to host overhead and the compress overhead, but not the actual handle.
we still have connect
Yeah,
to host.
that-
We still
cats-
take connect to host because you still want to take I/O here because connect to host is I/O.
Okay,
Yeah.
the problem is you've talked about there's a front end, the middle end, and the back end.
Right.
But you haven't said what the front end does, what the middle end does, and what the back end does, and you're assuming we know.
Right.
Okay, so you have the front end is only handling the targets, the physical connectivity
Right.
to the host. Then the
called the
logical,
by the way, to help you.
the logical layer, the most important, the metadata layer of the logical space, what we call the compute module or the C module, depends on the terminology. This is kind of what handles the addresses and everything,
Okay,
and
that-
snapshot
that
layers,
also- and that also does.
and this will.
the metadata handling and the
Yeah.
cache generation.
No, hash
Yeah.
generation.
Hash generation, it depends. It will happen in that layer.
Okay.
Later on, you have the backend where you have the hash space, and this hash space is attached to a specific set of drives.
Okay.
So obviously, the data eventually will get here and will be
I
written.
got it.
Yeah,
It's just the earlier explanation
Yeah.
sounded like if I did a rolling upgrade, the hash space would end up getting scattered across.
No.
No.
Hash space doesn't
Sorry.
move.
No,
And
no.
that would make your metadata.
Yeah, in that sense,
you don't want to do that.
Correct. This is very different from scale out in that sense.
Can I just ask a question? So going back to the creation of your hashes, I have
Yep.
two questions. First of all, is your algorithm that creates hashes mathematically guaranteed to create a completely balanced approach across all bricks?
Yes.
Yeah.
Guaranteed is a hard word, but SHA-1 does that pretty natively.
Guaranteed.
Is it SHA-1? Is it?
Yes,
you
a
guys-
version. It's a version of
It
SHA-1.
depends on the data, Howard. You can't guarantee it.
Yeah.
But so second, and also I'm assuming it's based on fixed blocks of what size?
16.
16K?
Yeah.
Was that an X2 change?
Yes. X1, X2. X1 was 8. X2 was 16. And we'll show you, Z will show you when we talk about write boost, that we actually did some interesting things that actually improve performance on all smaller block IOs. Because normally you think you make a bigger block size, your smaller block than that IO performance doesn't do
But
as well.
X1 was
we
orig-
actually are better.
X1 was originally 4, wasn't it? And then it went to
Originally, yeah.
Yeah, but then
It has also-
1.5 was.
Two
Yeah.
generations.
Yeah, two generations of software. I'm sorry, was there another question that I missed? Okay. Getting back to your original question, I haven't forgot it.
Yeah, sorry.
All right, so there's two permutations, right? So let me take the easy, I hope is the easier permutation. I thought the other one was easy, but that's okay. At first, let's add drives. So let's do this 18 and add 6 drives. So now I have 24 drives in the configuration. Think we move data?
I don't know. You tell
No,
me.
we don't. We don't move data because underneath the scenes, all we do is inside XtremIO, we basically, the algorithm says, all right, I'm going to look for the emptiest stripe. And by adding drives, I now have an empty stripe. So I don't actually move data around. There's no point in moving data around. There's no advantage from a performance point of view or from a capacity point of view to actually move the data around.
So the CAS extends to the brick, but not to the drive, as opposed to say solid fire.
Say it again.
The content addressability. So the content addressability is a pointer to a brick. It doesn't extend all the way down to the SSD.
No,
as opposed
the
to say,
drives, the XDP is a big pool of physical
as
capacity.
opposed to say a solid fire, where a drive in a node is
No.
responsible.
We don't want to have any bottleneck. We want to use all the resources evenly and evenly distribute.
Because what will happen is in this space is they will get, because they're emptier stripes and emptier stripes get new data, they will get more data, new data. So they will balance over time.
Yeah.
So rather than forcing the move for no real performance advantage, we just say let us just naturally let it happen. Yeah, does that make sense? All right, now let's take your real question, which was, I want to add an XBrick. So I'm going to add that XBrick here in the environment. So I say, all right, I'm going to add the XBrick in the environment, and I'm going to have 24 drives, because I've already added drives just to show you in the environment. All right, so here's the interesting thing that happens. So what we do from an OCE, or online cluster expansion point of view, is we go ahead and add the compute first, right? So if we think of the R, the C, and the D, we basically add and do these first. When we add these, we have the CPU. We have additional CPU right away. And then what we're able to do is, on the D point of view, we're able to reallocate the data across in the background. So we actually get more performance once we add the XBrick. And during the time of migration, we get as good or better performance as what we had before, because we have the additional CPU. And remember, SSDs, any type of all-flash array, your bottleneck is always the CPU. It's almost never the drives in the environment. So that's what we do. So for example, if this is, let's say here, I'm going to make my math good here. So if this is 90% full, and this is 90% full, I'm going to drain. I'll drain, and then I should go. I do my math right on my fly. I think I should be going down to 60%. Something like that. And we'll be rebalanced across the environment. That's an environment where we actually do move data, because we want to take advantage of the SSDs in this environment. So we do move the data.
So what triggers that move?
What triggers that move? The online expansion process is basically triggered in that we first add the it's a control event. So our professional services group, we go ahead and add the XBricks first.
Wait. Did you just say to add a brick to an existing cluster, I need professional services?
Yes.
Okay.
And if you still want to upgrade an XtremIO solution, you still have to call support as well.
Yes. It is on all of our high-end platforms. It is delivered 100% by professional services across all of our high-end platforms.
Can you talk about some of the automatic housekeeping processes that actually run as part of the XtremIO subsystem?
What would you mean by housekeeping process? I'm sorry.
CRC checksums go through cleaning, that kind of stuff.
I was going to talk about that a little later, but I certainly can talk about that.
If you're going to cover it later, we can.
Yeah, so I have a whole section high availability, and to me that all falls in high availability. So if you don't mind, if it's okay with you, I'll defer that.
Another quick question. So at the 40,000 foot view.
Yep.
So with the first generation of XtremIO, like for example the XMS, Extreme Management System, you could have a virtual appliance and also a hardware-based solution.
That's true.
Has that changed? Is that still the same?
Still the same. I will tell you, most of our customers are on virtuals, but you can have a physical as well. Remember that it's a control plane, right? So I think of it more like a Cisco SAN switch, right, or a Brocade SAN switch. You have the control plane and you have the data plane. The control plane can actually go away. And the I/O processing continues to happen. For example, if we're using replication, recover point replication right now, for example, replication still continues to happen. And when that comes back, when the XMS comes back, right, you just lose access. You have lost access to the control plane. Then we just go ahead and instantiate that. Make sense?
And what about
we actually automatically back that up as well too.
Right. And what about integration into the rest of the management ecosystem of EMC?
Sure. So we talked a little bit about, in the previous presentation, the VMAX presentation, we talked a little bit about Viper Controller, Viper SRM. We have full support for that. We have full support into VSI plugins for vCenter, vRealize plugins, also full support for that. Full support for Microsoft Hyper-V plugins. Let's see here, what else am I missing? Splunk support for that. And through EMC code, we have support for things like Docker and Cinder, Cinder support for OpenStack, for example.
So if I've got VMAX All Flash and XtremIO, I can use the same management components that I use for VMAX All Flash also with. You
can do it at a Viper controller level. You can abstract the layer if you want. That is possible. Yep. But that's primarily done for provisioning, right? So if we look at from a provisioning point of view, that's where you would want to go ahead and do that. From a element manager point of view, the element manager is different, right? They're not a common element manager between them. Currently.
And what's the limit for the number of XtremIO systems I can have with an XMS?
8.
8.
Yeah, that was same as X1 and X2. That has not changed.
So just to finish off on that one, there is some physical data movement. if you've got a reasonable degree of write activity, depending on what it is, there will be a natural sort of drift for the one that's more empty to fill up, because you'd be writing to that now, because a certain percentage by just maths would fall onto that.
Yep.
So how much of that are you letting just happen, and how much are you directing in the background as physical movement? Because there's a trade-off there that says, if as long as you're not massively full, if you were at 99.9%, it would be a problem. You'd probably want to move it. But if you're lower than that, you might want to just let that drift occur, because it would save I/O at the back end.
Do you want to answer that one?
Yeah. I think if I understood your question correctly, so I think there are two different aspects of it. So first of all, we are looking at we have different bricks. So each brick is responsible for the capacity it brings with it. And then you go and you take the entire hash space and you partition it into chunks, and each such brick gets the chunk corresponding to his relative capacity.
Yep.
Okay, so that's a fixed kind of responsibility for that state until you might scale out or something, and it means that any hash for each hash according to this partitioning, it will get to that place. It means that the portion of IOs that will go to that capacity element will be according to its ratio within the cluster.
Yep.
This doesn't relate to the fact that if those write are free initially and then they get full. So what happens? Let's go over Todd's example of scale out. So when we did this scale out operation, we actually told the system, okay, partition now the hash space according to the new to the portion of the capacity. So every 1/3 of the writes will get to this cluster, and these will continue getting also 1/3 of the writes. In the background, online, we have also the process that relocates all those hashes that have been here, and now, according to the new scheme, needs to move over here.
Yeah.
They will be moved along the time. Thanks to the fact that we added here a controller, the impact will be very low. We do it anyway very, very efficiently, so the impact on the user will be as low as possible.
So I get that, but some of those will occur naturally, because some of those will be rewrites of existing data that push that to that.
No, rewrite of remember, it's stored by hash now.
Oh, so it won't be then.
It's not a
So it has to be moved.
data. Well, yeah, and
But remember,
in
you said new writes go third.
Oh, now that's a real impact then. So every single write that potentially changes data is a completely new hash. So you can't expect that rewrite of existing data will actually dynamically move content.
No.
Because it will rewrite the. Yes, you're going to have to move
There's
it.
no overwriting in
Oh,
place.
that's-
It's
okay,
just
that's a big overhead.
logical adjustment.
Let me go with you. So if I have, for example, a rewrite of an address or something, so what is your question? Will I gain from the fact that I wrote
Yeah,
the
because you
data over here? So the answer would be yes.
Well, you will, yes. 'Cause
I
you'll
will gain that
indirectly, yeah, you will.
because what does it mean that I overload the data? Assuming it's not a dedupe, I will decref the data here
Yeah.
and write a new data here. So the data from here won't move, right? No
Yeah.
need. So you'll get it naturally.
Unless,
So
you're,
there's- so-
unless
so-
you're maintaining snapshots and
So I am right then.
But
So
then,
that-
then
so
it wouldn't
but-
be decreft because
so-
it has a
Yeah.
reference.
Sorry, just to finish it up, because I think this is quite important, but so I was right originally, sorry, Howard. But what that means is as you write data, the data will naturally drift to redisperse itself, simply because it's been rewritten. So there's a percentage of stuff that you just never need to logically move, because depending on the amount of write activity, it will rebalance naturally.
Yeah.
So then there's a question about if you weren't at that 99% full on the older blocks, if you're only at like 60%, then there's almost no need to rebalance, because it'll just happen naturally.
before you answer that question,
you could-
let me expound on it.
Yeah.
Because it's a content addressable back end, we add brick 3. Brick 3 gets is now responsible for a section of the hash space. Is that responsibility only on the read side, only on the write side, or on the read side? Because it seems to me that having hashes that brick 3 is responsible for that are on brick 1 because they haven't been moved yet would add complication to
But
read.
that's just a metadata read, though, isn't it? Surely.
It's a redirect node to node and
no.
InfiniBand latency.
Yeah.
No, you are right. So obviously reads that will come here.
Right.
We will find out that we don't have them and we'll need to relocate them. Okay?
Right.
So we do have.
Because it's content.
Well, there is that piece,
because
yeah.
it's content addressable.
Yeah, there is
you
that.
want to move the data.
The point is,
we don't want to stay in a state of where we haven't moved the data. We want to end up
Yeah,
in a balance, right?
If it was a more traditional back end, it would be much less important to move the data. That the things Chris is referring to
correct.
would
Yeah,
make a lot
because
more
we're
sense.
metadata-driven, content-addressable architecture.
Because it's content addressable architecture, and the content is in the wrong place, and therefore there's redirects. So I'm not.
Fine, let's move on, because
So
that's...
I'm not wrong.
I'm not arbitrating who's right and wrong here.
Oh no, we can fight that out amongst
to
ourselves.
say we'll have a discussion about that later, but no. So that I think you've answered what I was trying to get to.
Okay.
So rather than for the sake of things,
We're
I guess
deep
let's
enough.
carry on. Yeah.
So our goal eventually is to do balance the capacities. We need to remember that the capacity is not necessarily proportional in any way to the bandwidth you have, especially as you grow, you scale up the capacity. So maybe you don't increase your IOPS, but you do go up in capacity. And you want to reach a point where all the drives are evenly loaded and evenly busy, gets the same read to really have the full performance for the system.
Okay. All right, moving on. All right, I think we have actually talked through this pretty well on the slides, or on in the discussion, so I'm going to skip that. All right, so the data services, everything we do, always in line. That has not changed. That's true on X1, that's true on X2. We just did some little work on compression. All right, so what do we get from a performance standpoint, right? So certainly predictable performance, right? So this is an example of the web UI. I'll have a more longer session on it, but I just want to show you a little bit about this, right? So this is doing about, call it 68,000 and some change at 0.14 milliseconds. That's pretty good. Or 2.13 gigabytes a second. This happened to be booting desktops. Right, so 2,500 desktops simultaneously. I actually have a 4,000 example, which I don't think I'm going to get to. But you can certainly do a heck of a lot of, whether it's VDI or VSI, from a high performance here as well.